In the last class, we had discussed the scheduling policies for a real-time operating system, and we have found that we need to modify these policies or need to relook at these policies when there are processes sharing resources and there are conflicts regarding the demand of resources between these processes. Today, we shall look at resource management. Resource management involves scheduling for resources as well as strategies to be followed for special resources other than the CPU like memory as well as I/O devices. So, let us recapitulate what we did in the last class about the resource access. Many of the resources are actually mutually exclusive resources. Examples can be printers, examples can be sockets by which a system establishes network connection. These resources are allocated to a job on a non-preemptive basis. That means a process gets an exclusive access to the resource. And this resource demand and the conflict due to resource demand can actually cause deadline miss. And also, priorities of the processes that has been assigned depending on the periodicity or the deadline may not be valid and may not be schedulable according to these priorities because of these resource demands. So, let us look at this problem of what we call priority inversion. In this case, the priority of the task T1 is assumed to be greater than that of T2. Now, let us consider that T2 asks for a resource at this point. So, we are using P and V operations for gaining exclusive access to the resource. So, when it executes P operation, the task T2, since no other task is using that resource, it goes into what is called a critical section, that is the section in which it uses an exclusive access. So, it goes into the critical section, but now next what happens? T1 at this point gets scheduled, T1 starts execution, but the resource is still with T2 because it has not yet executed V, that is release operation. So, when this task T1 asks for the resource, it gets blocked and it waits, so it slips. And while it is slipping, the T2 really becomes able to be executed. So, T2 gets scheduled and it is now being executed. So, in this case effectively, although the T1's job is not yet complete, the T2 gets scheduled even though it has got a lower priority. So, this is an example of priority inversion. And the duration of inversion is bounded by length of the critical section of T2. So, when the critical section is over, it is released at V, okay. Then the T1 gets the resource, it executes in the critical section, then releases the resource at V, but it continues to be scheduled because its job is not yet finished, and then only after its task is done, T2 gets scheduled. So, this is according to the normal priority. So, what we find that when we require an exclusive access to resource, the priorities can actually get inverted. The problem becomes more complex if we have a number of processes demanding the resource, or if there are other processes as well in the system which may not be actually using the resource. So, here what happens is that priority of T1, we are considering a situation where priority of T1 is greater than priority of T2 and T2's priority is greater than that of T3. So, at this point, okay, the T2 is in execution, okay, and then the T1, since its priority, T1 comes in here, okay, but what happens is there is a PS that there is an attempt to get the resource, the P operation, okay, but that becomes blocked because T2 can already have the resource. If the T2 is having the resource, the T1 is blocked. So, T2 starts executing. So, here there is a priority inversion. Okay. But after that, the T2 blocks and T2 executes, but who is having the resource? The resource is actually with T3 because it has successfully executed the P operation. So, the resource is with T3, T1 is blocked, so T2 gets executed, but when T2 finishes its execution, the control, that is the CPU, is not scheduled with T1, but it's scheduled with T3 because T3 is having the resource and T1 is blocked for the resource to be released by T3. Okay. So, now T3 starts execution. Okay. So, once T3 finishes, then only T1 gets a time to execute. So, what it appears is that when there is a mix of such processes, that inversion period can be even more than that of the critical section. Okay. Because here what has happened is T2, since it has got a higher priority than that of T3 and since it does not require the resource, okay, it gets scheduled, okay, and T3's critical section period gets stretched because it is not getting the CPU. So, effectively T1, which is having a highest priority, gets blocked for a longer period of time. So, this is really a problem when your higher priority thread or the task is handling critical tasks. So, there has to be policies to overcome these problems. So, the most the simplest policy that we really have is what is called priority inheritance protocol. In priority inheritance protocol, what happens is when a job JK requests for a resource R, if R is free, it is allocated to JK, else JK is blocked. Now, this step is standard, which happens under normal conditions, but something additional happens in case of priority inheritance protocol. The job JL, which is blocking JK, now inherits priority of JK and executes with that priority. That means, in the previous example, T1 was blocked because T3 had the resource. T3 was having minimum priority, but because of priority inheritance, now T3 will having the priority same as that of T1. That means, T3's priority will be more than that of T2. So, it will finish off its critical section earlier. So, what we say, since the block process had the highest priority, the blocking process inherits it. So, overall execution time should reduce. So, the period for which actually the priority inversion takes place would be small enough. But obviously, this cannot prevent deadlocks. When can deadlock happen? When processes are looking for multiple resources. Okay? And if process or the task T1 has resource R1 and is looking for resource R2, and the process or the task T2 have the resource R2 and is looking for R1, there would be a deadlock. Even priority inheritance cannot eliminate deadlock situation. There is another protocol which is better because it can manage things in a more appropriate fashion, is priority ceiling protocol. Now, here what is the assumption? The maximum resource use is known. Okay. So, in fact, if I know the maximum resource usage, there are algorithms and techniques by which I can schedule the resources so that deadlock do not occur. So, that means I can prevent deadlock. So, under similar assumptions, priority ceiling protocol works. That means it assumes that maximum resource use is known, and it introduces two entities, two quantities, pi r and pi hat t. What is pi r? Pi r is a priority ceiling of resource r, and it is the highest priority of all the jobs that require r. Okay, because since you know the resource use by each and every task, so you can compute pi r because this is a priority of all the jobs that require resource r. And pi hat t is a current ceiling of system. It is equal to the highest priority ceiling of resources in use at the time. That means there may be a set of resources which are in use, and that priority ceiling or the current ceiling would be equal to the priority of the maximum priority of the resources which are currently in use. Then what is done? At release time t, a job starts with its assigned priority, because there is a priority defined by the scheduler. When a job jk requests for r, that is a resource r, if r is not free, jk is obviously blocked. But if r is free, r is not straight away allocated. What is done? What is checked is if pi t, okay, is greater than pi hat t. Pi hat t is the priority ceiling, pi hat t, then r is allocated to jk. Else, if jk is the job holding the resources whose priority ceiling is equal to pi hat t, then r is allocated to jk, else jk is blocked. What is the motivation of this? Motivation is the job is having higher priority than that of the priority ceiling. That means it is more important than the jobs which are currently using different resources. So, the resource should be granted to the requesting job. The other scenario is that current priority ceiling may be because of usage of the resource by the current process itself, okay, although its current priority may be less or equal to that of pi hat t. It should be equal to pi hat t. So, under that condition, it should have the resource, because if it has the resource, then it can finish off the job and can release the resource for others. Otherwise, it will continue to get the continue to wait to get the resource. So, the resource gets allocated to jk, okay, and the blocking process inherits the highest priority of the blocked process. If there are multiple such blocked process, it gets the highest priority. This is same as that of priority inheritance. So, therefore, priority ceiling protocol is an improvement upon your priority inheritance protocol. What is the implication here if you look into it? The basic implication is that depending on the priority of the resources which are in use, the resources are getting allocated. Resources are not just getting allocated on the basis of their availability. So, what is being ensured? A process with a higher priority will get the resource and will finish off its job earlier than other processes. So, let us take an example to understand this. So, I have got these jobs J0, J1, J2, J3, and the priority of J0 is greater than that of J1, greater than J2 and that of J3. Now, J2 books R2, okay. So, what will be the pi hat t? R2 is a resource, will be that of J2, priority of J2, and J3 requests R1, okay. So, pi hat t now is greater than that of J3. So, J3 will get blocked, okay. Now, J1 requests R1. Now, pi hat t is that of J2, which is less than that of priority of J1. So, R1 should be allocated to J1, and now the priority ceiling becomes that of process J1. So, J2 now requests R1, okay, but J2 will be blocked because currently its priority less than of that of a priority ceiling, and J1 requests R2. So, pi hat t is equal to priority of J1. So, R2 will be allocated to J1. You can understand that if I would have allocated here, okay, the J2 is not possible to complete its job because it is requesting R1, and J1 is requesting R2. So, it is getting all the resources because it is of the highest priority, and J0 requests R1. When J0 requests R1, this pi t is greater than pi hat t, but J0 does not hold any resource. So, J0 is blocked. So, this is a current subtlety which is there in the priority ceiling protocol. It enables a process which has got the resources to finish off its task. Okay. So, the resource does not get allocated to a process because of its higher priority only. If I would have allocated that, this might would have led to a deadlock situation, okay. And J1 inherits priority of J0 because J1 is blocking J0. So, J1's priority increases, so it is likely to finish off faster. So, this is how you manage the resources based on the priority associated with the processes when the processes are competing for the shared resources and resources need to be allocated as an exclusive resource. In fact, this is a very critical problem in variety of embedded systems, okay? Because if the blocking is larger, then there may be critical deadlines can be missed, and accordingly there could be bug or the faults plugging the system behavior. It may actually detrimentally affect the system behavior. So, how do you calculate the duration of blocking? When resource access of preemptive priority driven jobs are controlled by the priority ceiling protocol, a job can be blocked for at most one duration of one critical section. Okay? An upper bound on blocking time can be computed and checked for generating feasible schedules, because you exactly know why this is possible. This is possible simply because you know the resource usage beforehand. So, you know the priorities to be associated with the resources. And why the first condition becomes true? When resource access of preemptive priority driven jobs are controlled by the priority ceiling protocol, a job can be blocked for at most one duration of one critical section. It cannot be blocked for more because the resource is getting allocated to the job which is having the priority ceiling, and it is having other resources as well, and it will not get blocked because of the processor being allocated to another process, because it will inherit the priority of the highest blocked job. Okay. So, these are the advantages of priority ceiling protocol, and in fact, this is better than that of your priority inheritance protocol. So, we shall look at a case study to understand this priority inheritance and the priority inversion, how it creates problem, and this is a real life problem which happened with Mars rover Pathfinder. Okay. This is it was a mission in 1997. So, what it says is that it gathered transmitted voluminous data back to Earth, including panoramic pictures that were a bit hit on the web. In fact, on NASA website those pictures are even today available. But a few days into the mission of gathering meteorological data, Pathfinder started experiencing total system resets, each resulting in losses of data, because whatever data is gathered, if the system gets reset, then there is a loss of data. The whole software was working on a operating system, a commercially available operating system, VxWorks. And VxWorks, this is an operating systems. VxWorks implements preemptive priority scheduling of threads. Tasks on the Pathfinder spacecraft were executed as threads with priorities. Priorities were assigned reflecting the relative urgency of these tasks. This is a standard way of assigning priorities. And why threads are being used? Because I told you that threads in an embedded system is the most likely mechanism to manage concurrency, because the context switching overhead for threads is much less. So, Pathfinder contained what is called an information bus, which was a shared memory area used for passing information between different components of the aircraft in the spacecraft. See, basically these processes, threads, also need mechanisms for communication. Shared memory is one mechanism for communication between threads as well as that of the processes. So, that shared memory is being referred to as information bus. Obviously, the access to the bus was synchronized with mutual exclusion locks, just like our P and V that we are using, because there cannot be more than one process using the data which is there in the shared memory area. So, we shall look at three basic tasks and how they interacted in terms of their access pattern to that shared memory. A bus management task ran frequently with high priority to move certain kinds of data in and out of the information bus, okay? Because this is a bus management task. Okay? This is basically managing what is so called information bus. The meteorological data gathering task ran as infrequent low priority thread and used the information bus to publish its data. Okay? and communication task ran with medium priority. In fact, communication task, if it is communicating meteorological data, it will access the information bus to get that data. So, there are these three basic tasks. These task was high priority task, okay, and in fact it is a critical task, okay, and this is a data gathering task and this is a communication task. Now, there is a priority inversion. Why? While meteorological task had lock on information bus and was working on it, an interrupt caused the bus management thread to be scheduled. Bus management there can be an interrupt because of, and bus management thread is of higher priority. The high priority thread attempted to acquire the same mutex in order to retrieve published data, but would be blocked on the mutex waiting until the meteorological thread finished, because it has now gotten exclusive access to that shared resource. So, now the priority gets inverted. But things were fine. Most of the time meteorological thread eventually released the bus and things were fine, because your bus management thread got back the information bus, the shared memory, and managed the systems well. But at times, while the low priority meteorological task blocked the high priority bus management task, the medium priority communications task interrupted and started running. It can start running and do jobs for which it does not require information bus access. Okay. This was a long running task and hence delayed the bus management task further. Okay, when as long as it is not requiring information bus access, it can continue to run, and it is managing basically the communication link with that of the earth station. So, what happens? Every embedded system has got a watchdog timer. Okay. So, after some time a watchdog timer sensed that the high priority bus management task has not run for quite some time, because it's, if I have programmed it for a certain time period, once that time period expires and it is and the high priority task would be given the job of reinitializing the watchdog timer. So, watchdog timer is not getting reinitialized. Okay. So, that means system has gone into some kind of an unknown state. Okay. So, something must have gone wrong drastically and you reset the system. Okay. So, what I was trying to illustrate with this example is how the different components in an embedded system are interdependent and they can interact, and if you do not take care of all their possible interactions, this can be also source of bug. So, debugging in such a case becomes extremely difficult. Okay. You have to do actual execution traces, follow the execution traces to reproduce the scenario and identify the cause, and these effects occurred when the rover was actually on Mars. And you have to have a complete simulation environment in the earth station to identify the fault and try to rectify the fault. Now, what was found out was that priority inheritance had been turned off. Okay. Since priority inheritance had been turned off, because priority inheritance means what? Again a kind of a scheduling overhead. In order to save time, you have turned off the priority inheritance. So, had it been on, the low priority meteorological thread would have inherited the priority of the high priority bus management thread, that is blocked, and would have been scheduled with higher priority than the medium priority communications task. Okay. On finishing, the bus management task would have run first and then the communication task. So, the priority inversion period would not have been elongated. Okay. Because it was elongated, watchdog timer was finishing its count. Okay. So, and that is how the system was getting reset. In fact, it is a very well known problem, okay, which is cited for illustrating these problems which gets associated with resource allocation and resource scheduling and the priority assignments depending on the task characteristics. Now, we shall look at another kind of applications, okay, which we say flexible applications. Okay. Many applications are flexible in the sense that you can actually accommodate what we call graceful degradation in result quality or in timeliness. Okay. So, that means what we are talking about is, so far we had talked about soft deadlines, hard deadlines. Soft deadlines, I said, we can miss sometimes, but here we are introducing a concept that we may still meet deadline, but the quality of the result may be poor, or we may miss the deadline, but still ensure quality of the result. Now, this kind of flexibility is not there for each and every kind of job. For some kind of tasks, this kind of flexibility would be there. So, what do we say? Applications are designed and implemented to trade off at runtime the quality of results or services they produce for the amounts of time and resources they use to produce the results. So, if it becomes a kind of a parametric trade-off, the scheduler can look at this trade-off and accordingly schedule the time, that is processor time, as well as other resources. So, how do you characterize flexible applications? A flexible job typically has an optional component which can be discarded when necessary in order to reduce job's processing time and resource demands by deadline. Okay. If I talk about firm deadlines m, n, what is the definition of this? If at least m jobs among any consecutive n into m jobs in the task must be complete in time. So, this is a kind of a deadline which is getting specified. Okay. And n is actually the failure window of the task. Right? So, what is the criteria of optimality under these conditions? The kind of errors that can commit, the rewards corresponding to for some of the tasks meeting the deadlines and the quality parameters. Then you have got static quality metrics, and there could be dynamic failures and requirement to meet this kind of firm deadlines. So, we say that there is a trade-off between quality of service and timeliness. Okay. So, how the parameters are related, one is called firm quality and firm deadlines. For a firm quality, you have a fixed resource demands, okay, and degrade gracefully by relaxing their timelessness. Okay. That means we are still not compromising on the quality, okay, but we are compromising on the deadline. And on the other side, I can have firm deadlines. What does that mean? There is a flexible resource demands, but hard deadlines. You degrade gracefully by relaxing the result quality. Okay. If we take a simple example to understand this, let us consider the job of decompressing a video sequence. Okay. Now, when I am doing decompression, the complexity would be what? Dependent on the decompression overhead. Okay. Now, if the image, let us consider a frame is divided in terms of blocks. Okay. And now, if I actually do decompression for all the blocks of the frame, I get good quality output. Now, it may so happen that I may not be able to meet the deadline if I am trying to decompress each and every block. So, I can compromise on the quality. How do I compromise on the quality? I simply copy blocks from the previous frames. I do not decompress each and every block in the image. I simply copy blocks from the previous frame, or I just interpolate blocks from the decompressed blocks in the image. So, here I am meeting the deadline, but compromising on the quality. On the other hand, what I can do? A video compression task has got soft deadlines. So, I can afford to miss the deadline, okay, by small amount, and by missing deadline, what I shall do? I shall decompress all the blocks and generate good quality frame. So, this kind of trade-off is there for the flexible jobs, and scheduler needs to take account this flexibility while scheduling tasks. So, what are the different kinds of policies the scheduler can adopt? One is the sieve method. Sieve method is the simplest part. That is, when a scheduler finds during schedulability check that this deadline cannot be met, so the optional part of the job is discarded. Okay. The optional part of the job is discarded. So, the computation time decreases, and under that condition it should be possible for the scheduler to generate a feasible schedule. The other methodologies are milestone method, multiple version method. We shall look at them, and the very common use of these kind of flexible tasks are related to multimedia communications and computation tasks. In fact, majority of your multimedia enabled devices like your cell phone, your VCD player, MP3 players, MP3 player with added functionalities which are coming into the market, all of them implement some variant of this kind of flexible scheduling policy for dealing with resources. So, what is a milestone method? Okay. In a milestone method, you deal with what are called monotone jobs, a job whose result converges monotonically to desired quality with increasing running time. Okay. So, that means if I stop at any arbitrary point in time, I shall get some result, but I shall not meet the quality. So, a monotone computation job is implemented using an incremental algorithm whose result converges monotonically to the desired result with increasing running time. That is basically characteristics of a monotone job. So, how does the monotone for a monotone job this is implemented? So, designer identifies optional parts of the program and quality criteria. I had already talked about the quality criteria. During execution, intermediate results are saved with quality indicated. It may be a least mean square error etc. or any other error measure for that matter. And runtime decisions to schedule processes are taken on the basis of current quality of results. That means, scheduler looks at quality of the results, okay? And on the basis of that, it decides whether this can be further scheduled or not. If there is some kind of slack window available, it will schedule the job once a particular quality is reached. So, what you find, depending on the job mix, the quality of the result can actually vary. Then you have got a multiple version method. Each flexible job has a primary version or one or more alternative versions. Primary version produces precise result, needs more resources than execution time. Alternative methods have small execution time, use fewer resources but generate imprecise result. In fact, these multiple version methods have come in with the concept of what is called scalable coding for multimedia data. Okay? When you really using any kind of multimedia transmission, there can be a base level coding as well as there can be an enhanced level coding. Base level coding, a simple example could be that if I am using a video phone telephony application, in the base level I can have a subsampled frame. I am transmitting at the base level subsample frame. When I am transmitting subsample frame, I am requiring less bandwidth, bandwidth is a resource. I shall require less processor time to actually show the image. So, that is a base level. And you also have an enhanced layer. Enhanced layer is the error between the actual frame and the subsample frame, and you transmit that in enhancement layer. So, you have got multiple versions. So, if you have the resource, if you have resource to accommodate the enhancement layer, you get the enhancement layer as well. If you do not have a resource, you do not use the enhancement layer, you can discard the enhancement layer. So, that is a multiple version method for dealing with flexible jobs for resource allocation. So, scheduler chooses version according to available resources. Okay? So, whether it would accept, for our example, accept the base layer or the enhancement layer, and set of jobs are scheduled together for the optimal quality. So, this more or less finishes our dealing with resources in a generic sense. Okay? So, how resources are managed. We have looked at when there is a conflicting demand for a resource, how the priorities have to be dealt with. We have looked at when there are job characteristics as such that the resource usage can be made flexible, how that flexibility can be exploited for scheduling the resources. Now, we shall look at features of two basic resource, okay? One is memory, another is generic I/O devices. The memory management typically in an embedded system involves, and an embedded OS involves managing a variety of data structures, okay? Because primary job is that of managing memory allocation between concurrent tasks. And in fact, when we looked at the memory management unit in the context of ARM, we have already seen that one job of MMU is to provide protection to the memory areas allocated to different tasks. The data structures which are used for this purpose, in a generic sense we say region table, page tables and kernel map. Region table is an array of regions that track the allocations of all the physical memory in the system. Page table is each process belongs to a protection domain that is defined by the page tables that are associated with the process. In fact, each process has got associated with a page table, and that can be associated with a protection domain. That means the protection features with the pages allocated to the process. Then there is a concept of what is called a kernel map. Kernel map is a list of mappings that are entered into all the page tables in the system, but are accessible only when the CPU is in supervisor mode. What does that mean? See, kernel itself of the OS will map onto a set of pages. These pages are made part of the page table of each and every process. Why should you do that? Because processes can need to make call to the OS. Okay? So, in that case you need not do a explicit context switch. What you can actually do is use these pages, but the protection comes in place because these code which are in these pages are executed only in supervisory mode. A region is a basic unit of memory allocation, okay? And a region typically is defined as a page aligned contiguous sequence of addressable locations that are tracked by a starting address and the length, and that must be multiple of page size. So, actually you will find this region how it comes in a, if you remember in context of ARM we talked about sections, okay, and these sections in a generic way we are referring to as regions. The entire physical memory on a given machine is managed using a boundary tag heap. We had talked about heap in the context of a process. Now, OS has to manage the complete memory area for allocating memory to the different processes. So, how does it manage that memory? It manages that memory again using a heap like a data structure, but heap now stores basically the region data and the region information. And the region typically in a paged memory system would be size would be what? A multiple of the page. Page tables are records kept in a typical singly linked list, and page tables are arranged contiguously in memory corresponding to a process. So, using all these data structures fundamentally and the most importantly in an embedded system, which service is provided? It is a security service. So, that one process cannot actually destroy or corrupt memory of some other process. So, two issues is there, therefore, limit access by one process to the memory regions of other processes and limit access by user processes to kernel memory. And the memory protection scheme today, if it is at all implemented in embedded system, in majority of the cases exploits the MMU hardware, okay. And virtual memory management may not always involve swapping. Now, in this case, because in many embedded systems you really do not have secondary storage like disk. The swapping I had already discussed earlier, the swapping can be between flash and the RAM, okay, and if at all there is a disk between disk and the RAM. But in many cases the swapping part of the virtual memory management system is not implemented. What is primarily made use of is the protection mechanism. So, if you go back to ARM and recap what we had talked about, the ARM MMU actually provides for this. So, OS actually does what? Has the code for running the different functions that MMU offers. Okay. If you remember that it presents ARM MMU can manage 4 GB address space depending on the size of the address bus, and memory granularity is 3 options: 1 MB sections, large pages, small pages. So, these kind of pages, collection of pages or sections are being referred to as regions, okay, and region can consist of a number of pages, and OS keeps track of the regions and the pages for the purpose of allocation to different processes. And what does MMU do for protection? It defines what are called various kinds of domains, and using domains actually this protection policy is implemented. Apart from that, these other tasks which are done through MMU is when there is a virtual address involves virtual memory and the swapping between a secondary storage and the primary storage like RAM. So, a processor puts a processor what we say in abort mode when virtual address is not mapped to permission check fields. So, that is an abort mode of ARM. So, OS has to provide the code for the abort mode for actually page transfer from secondary to primary memory. Okay. So, this part of the code will run in the abort mode. Other thing is for normal task management, change pointer to page tables called translation table base, because this happens when process switch takes place, because it will switch from one page table base to another page table base, and page table bases are managed by the MMU. Now, we come to the domain based protection, because MMUs also provide the domain based protections. Okay. In fact, domain is a set of memory pages that are mapped using a set of page tables. Okay. A set of memory pages associated with the operating system kernel is called kernel map. The kernel map is mapped into all domains, but is accessible only in supervisor mode. Result is that system calls require only transition from user to supervisor mode rather than a full context switch. This point we had already touched upon. But what is the basic concept of domain? Domain is each process is basically a collection of pages which can include pages belonging to other processes like kernel of the OS. Now, therefore, that set of pages are associated with a domain based protection. So, domain defines the protection features, the access rights. Okay. So, that gets defined associated with the domain, and MMU checks that whether you are when you are accessing pages which are belonging to a domain, whether the process is violating any of the domain related access control conditions. So, domains control basic therefore access to virtual memory by isolating one area of memory from another when sharing a common virtual map. In fact, there are 16 different domains that can be assigned to 1 MB sections of virtual memory in ARM. So, these are the different kinds of protection scenarios which can be implemented by the OS on the virtual memory. So, basic operations for the domain is insert the mapping of a page into a domain, remove the mapping of a page from a domain, insert the mapping of a page into kernel map, remove the mapping of a page from the kernel map, update a domain to reflect the current mappings in the kernel map. So, that means there can be pages now belonging to different processes. So, you can consider even if there is a shared memory, just like information bus we are talking about for the rover, that shared memory would be again a page which may belong to multiple domains for the purpose of an exclusive access. Okay. But this, when that access takes place, there is really no context switch, but access may take place depending on where and how that shared memory is being managed. If it is part of the kernel, the access can take place via the kernel map. Cache management is another important aspect of the OS. Okay. One of the issues of this cache management is that when we had looked at the question of computation time, and you can understand the computation time of a process can actually vary depending on whether the process is in cache or not. Now, we may like to optimize on this computation time. So, we may decide to have a clean partitioning of the cache memory, and so I can have locking facility in the cache memory. So, lock facility is there, lock facility can be in the hardware, but it is managed by the OS, and in the design time you may decide that this task is a critical task and hence it should be locked in the cache. It may be a kernel task, maybe the scheduler which would be locked permanently in the cache so that it is never swapped out. The other resource which is to be managed, because since our embedded system is situated in an external environment, it needs to deal with variety of I/O devices. So, managing I/O becomes a critical issue. In fact, I/O devices can be categorized into various categories, okay, because their management also varies on the basis of their need. So, Human readable examples are printers, video display terminals, which has got a display, keyboard, mouse. All of these are I/O devices. And these kind of devices you encounter not only on general purpose computers, but if you are looking at embedded systems like Sony Game Station, video game systems, there also these kind of devices are to be managed. Printers are typically you will find in point of sale terminals. Okay. There you have got small printers, okay, for doing calculations and providing the receipts. ATMs have got printers for providing the receipts. So, it is not that these kind of devices are only found with general purpose computers, but also on embedded systems. So, we need to know how to deal with these kind of devices. There are machine readables, okay, sensors, controllers, actuators, they are more common with the embedded systems. Disk and tape drives are obviously not that common, but disks are also there in a variety of forms with since the size is reducing and the storage is increasing. And then communication devices, which are primarily to communicate with variety of things. So what we are looking at? We are looking at three categories of devices. Why these categories are coming in? Because of their nature of the functions that they operate, the nature of the data that they handle would be different, and accordingly the interfaces have to be designed. So, the differences really come in several orders of magnitude between what we call data transfer rates. Why this data transfer rate is important? Because this data transfer rate is related to interrupts that this device can actually generate, and you have the processes which are also running. Is it that will you permit interrupts to interrupt execution of a critical task for each and every data transfer corresponding to a high speed device? That is the decision that the OS has to take while designing the software. So, there would be complexity of control related to the device, and the key issues are unit of transfer. The data may be transferred as a stream of bytes, maybe it may have as a blocks like it is transferred from a disk. Then you have got encoding schemes as well as error conditions, because devices respond to errors differently, and on an embedded system you have to have provision for taking care of these exceptional conditions. And typically you have programmed I/O and interrupt driven I/O, because your interrupt device interfaces therefore has to cater to these two requirements, as well as if there is a DMA. Okay, how does a DMA gets initiated? DMA gets initiated by enabling the DMA controller. Who enables DMA controller? A kernel level task. So, OS has to know how to initiate also the DMA. It has to, these interrupt driven IOs will have associated with it ISRs. These ISRs are also part of your OS, and programmed IO, these are also part of your OS. So, broadly if you look at these kind of functionalities, the devices we can put in these three categories. Character devices can be accessed as stream of bytes, it can be a typically console. Block devices allow transfer of blocks, typically disk. Network interfaces, typically communication devices, device that is able to exchange data with other hosts, not stream oriented and hence not easily mapped into what we say in a file system. Now, you have got the device driver. So, all these things are managed basically having device drivers. Device drivers provide what? The software layer between applications using the device and the actual device. And we had actually seen that each device has got its own typical characteristics. So, OS has to provide for this kind of device drivers catering to needs of each and every device. So, device drivers implements kernel code to access the hardware. It handles concurrency between multiple simultaneous accesses, okay. But it does not implement policies about usage, because these policies comes from where? From the resource scheduling, okay. So, resource, we had already talked about resource scheduling policies in terms of say priority ceiling, priority inheritance. That is not part of the device driver. Device driver just provides a interface. So, basically these device drivers should be written in which way? They should have some kind of a generic capability. There are generic device drivers. desirable to handle generalities, that because we need to handle all I/O devices, we would like to handle I/O devices in a uniform manner. So, in that case, you hide most of the details of device I/O in lower level routines, so that applications can use read, write, open, close, lock, unlock, lock, these kind of top level routines which are not really concerned with details of the device. Efficiency is also an issue, and this is a key issue. Why? Because most I/O devices are extremely slow compared to main memory. Okay, even if you have got a first device, they are slow. And use of multi-programming allows for some processes to be waiting on I/O while another process executes. So, blocking can happen when you are not being able to meet the requirement of the data of a process from a device. In fact, typically all device access requests give rise to blocking. Okay. And swapping is used to bring in additional ready process which is an I/O operation. If you see swapping, if you are doing it from flash or from a disk, can be actually considered as an I/O operation. So, what you do is the very basic policy that OS adopts for interfacing with these devices is buffering, okay? And these buffers are actually managed through your device drivers. So, processes must wait for I/O to complete before proceeding, but if you can use a buffer, what do we say? The buffer decouples the time for processing from the time of input and provides a computable upper bound on the time required to service an interrupt. Because if you actually have a buffer, if I consider a communication device is getting the data and writing onto the buffer, okay? And when a buffer is full, okay, a communication device may be generating an interrupt, okay? So, the device is not generating an interrupt at each and every point in time when it is receiving a data, okay? And there could be variety of buffering schemes, because these buffers are again resources which are managed by the OS, okay? So, this buffering can be block oriented or stream oriented. Block oriented because you have got devices which are block oriented device. So, in this case informations are stored in terms of blocks and transfers take place in a block. Stream oriented is when information is transferred as stream of byte for terminals, printers, communication ports, etc. Now, this buffering can also come in variety of ways. The simplest is single buffer. Operating system assigns a buffer in main memory for an I/O request, okay? So, in a block oriented device, what happens? The input transfers are made to the buffer and block is moved to user space when needed and another block is moved into the buffer. So, you are doing a read ahead. Now, how this movement takes place? This movement means if the buffer is a page, you just alter a page table entry in the page table of a process. If the process has asked for a data from a disk or maybe from a flash, you actually get the data onto a buffer, okay? That data transfer, now you can consider, I can use simply a DMA to do this transfer. When a DMA is doing this job, processor is not at all involved. But what processor has done? Processor has allocated that buffer. When the DMA is complete, what happens? DMA controller generates an interrupt. When DMA controller generates an interrupt, the interrupt service routine can actually do what? Depending on which process has asked for the I/O, can make corresponding entry in the page table. Once it makes entry in the page table, the domain based protection comes in place. So, this data is also gets protected from unauthorized access from different processes. This block oriented, so what we say, the user can process one block of data while next block is reading, because the moment one block is allocated, block is given, another block the OS can make schedule. Swapping can occur since input is taking place in system memory and not user memory. An operating system keeps track of assignment of system buffers to user processes. That is how exactly the page table modification is done. Now, when it is a stream oriented, different from block oriented, what happens? You used a line at a time. So, user input from a terminal is one line at a time with a carriage return signaling the end of the line. So, output at the terminal is also one line at a time. So, for each character, so if you consider a keyboard interface, it is not that for each character actually the data is read in. You allocate the buffer of a size and you do the read in when there is a new line. So, that is basically the typical feature of a stream based interface. And if you remember, we said that we have classified what? Basically the devices as block based, stream based. So, when I have a stream based buffer, so the buffer management is stream based. Okay? And who manages the buffer? The device driver corresponding to that device. Okay? In fact, the interrupt service routine, when it comes in, that becomes part of your device driver. In many cases, you use double buffer, use two system buffers instead of one. So, a process can transfer data to or from one buffer while the operating system empties or fills other buffer. Okay, because it can be, therefore, buffer actually becomes time shared, because what happens? While one buffer is being filled up, okay, for a normal case, the process which has requested the I/O is blocked till the buffer is full, okay, and the buffer gets transferred, it will cannot access. But if there is a double buffer, then both operations can take place simultaneously. Okay. So, in fact, providing the next buffer is almost similar to that of a double buffer, but double buffering means that at any point in time, two buffers are typically allocated. In a single buffering, one buffer is allocated, and once there is a mapping of that one buffer to the user process, the next buffer gets allocated. This can be done also through circular buffer. Okay. More than two buffers are used in case of a circular buffer, and each individual buffer is one unit in a circular buffer. So, if it is a continuous stream of data, okay, when you use a circular buffer, effectively you are giving an impression of an infinite storage, because you are entering data from one end and going through just like a circular queue. So, that kind of a continuous stream of data management becomes easier. So, if you are talking about a kind of a speech interface for a cellular phone, the buffer allocation for the receiver would be a circular buffer, because you really do not have an idea of what will be the length of data, and it will be a continuous process. Okay. So, this buffering is the key issue in terms of generic aspects of I/O management, and other aspects becomes device specific. So, we have studied basically the resource management, primarily scheduling of resources, memory, as well as that of I/O. In the next class, we shall look at organization of a typical OS which is targeted for embedded appliances, okay? As well as we shall study the issue of power management, because so far we have considered memory, we have considered I/O, we have considered processor for the purpose of allocation, but power is also a very important resource in an embedded system, which is not true for a general purpose system. So, we shall look at that point in the next class.